Okay, lifting fan selection. So this is basically what we did in class. We're going to go over it in same level of detail, but this allows you to watch it again and again and again just to make sure that you get it straight, because this is the most important calculation you have to do for the semester. So there are 8 steps. Now the first thing I want to talk about is that what I mean by why I color some of these words red and some are black. Whenever there's a red word here, that means that something is not necessarily set in stone. That's something you have to choose. So when I say estimate the weight of the craft, that's something that's up to you. You have leeway, and you may end up with different numbers than somebody else. Or choose a desired gap size. There's no right or wrong answer. We want something between 3 and 5 millimeters. But you can go a little bit more or a little bit less. When I say calculate, for example, that's not red. So calculate, there's only one way to do that. So there's definitely calculation. There's one particular way to do that. So these red ones are ones where, because there's wiggle room or variation, your design's going to end up different than somebody else's because of these 4 red words here. And finally, also, if it's not possible, this at the end we'll find here that we may have to iterate and do something over and over and over, or we have to make a decision about if you can't find an appropriate fan, what are we going to do? So this is a decision point. So again, these red ones mean that there's no real set way of doing or set answer, no right or wrong answer. There are good answers and bad, but there's those kind of gray zones in there. So that's where we go. So anyway, step one. Step one is estimate the weight of the hovercraft. So basically what I've done here, and I got a little spreadsheet, and I've said, okay, I have some lift fans, and I'm going to 2 there, and I don't know how much they weigh yet, but I'm going to guess they're about a little over half a pound each. So 2 of those weighs 1.2 pounds combined. I have a fuel cell and connectors, and we actually did weigh these. It's about just under a quarter pound. NXT and batteries, so again, I actually weighed these for you, so it's 0.71 pounds. AA battery packs, this is roughly what an 8-pack of AA batteries weighs, and I said, well, I didn't know about my decks, so maybe 0.2 pounds, and sensors and relays. I was estimating. I didn't really actually weigh these, I just kind of estimated them. But anyway, for the purpose of the example, I ended up with an estimate of 3.03 pounds, and your estimate's just somewhere being in that range, 3 to 5 pounds. 5 pounds kind of the upper end, 3 to 2 or 3 is getting, it's pretty hard to get it below 2 pounds. So 3, 4, 5, that's pretty common. So I've estimated the weight, and again, this is my initial estimate. I don't know how many fans I need. Well, I'm hoping I only need 2. If I get done I need 3 or 4 or 5, I have to go back and change my design. But right now I'm going to estimate that I need 2. I'm estimating that I'm going to use, I have a 0.2 pound deck and so forth. So these are my estimates. This is my best guess at this point. Okay, so step 2. Step 1, I did that. Step 2, I'm going to choose a desired gap size. So I'm going to choose a desired gap size here. I'm going to use 0.2 inches. That's 5 millimeters. We said you want between 3 and 5 millimeters. I'm going to choose the upper end because that gives me the most. I mean, if I said I want to hover 10 feet, I'm going to need a lot of power. If I want to hover 5 millimeters, that's kind of the upper end, the extreme amount of hover that I might need. And so it allows me to back off. So if I end up needing, I originally estimated 2 fans here. So if I end up needing 3, that gives me backing off. I can back off to maybe 4 millimeters or 3 millimeters. So I'm going to estimate in the upper end, kind of worst case scenario. Planning for the worst case scenario is what you can think about it. So the air cushion is underneath the hovercraft called a plenum. So imagine I take this bowl and I flip it upside down. That bowl is what's going to hold my pressure. I'm going to pressurize that bowl, and that's going to get me off the ground. That's called that bowl is that cavity by having a bowl upside down is called a plenum chamber. We talked about having these meat trays. You can get like a chicken, when you buy chicken or ground beef at Safeway. These styrofoam trays that the meat comes in. If you flip one of those upside down, that little cavity would be called a plenum. And that's what I want to pressurize. By having pressure in there, that's going to get me off the ground. Now, when this whole thing, imagine this meat tray or bowl lifts off the ground, there'll be a gap all around the bottom of this plenum. And the gap is between the plenum and the ground. That's the gap size. How big do I want that gap to be? How high do I want my hovercraft to be off the ground? And I want that to be about 5 millimeters. Now, if it's too small, you get stuck on any bumps, and we're actually going to have some speed bumps. You get stuck on them. And also, when you tilt your hovercraft, when your hovercraft tilts to move, for example, or turn, you actually one end of the hovercraft might drag on the ground, or actually she might actually nosedive or dig into the ground. If the hovercraft is too big, one, you need big fans. That's because you're trying to hover higher. But 2, actually, when you have very little friction, it gets very hard to control. So you don't want to be too high. So 3 to 5 millimeters is what we're asking you to do, and that's based on our experience. So, all right, so that's step 2. That's chosen. These 2 things are totally up to me. Step 3, I'm going to choose the shape of the deck. So I have to choose the shape of the deck: rectangular, round, other. People do tombstones, triangle, wedge shapes, whatever you want. And you can have some reasoning why you want to do rectangular versus round or other. And your team will have to decide what shape they want. For this example, I'm going to use a square. It's just an easy one to do the math for. If you want to do a tombstone or wedge shape or trapezoid, the math just gets a little more complicated, but it is doable. So let's go ahead and use a rectangle for now. Actually, a square for now. So I'm going to, step 3A is I have to estimate the size and length. So I'm going to say estimate 24 inches right now. So I got a square which is 24 inches on a side, and that allows me to calculate the perimeter and the area, basically. So obviously the perimeter is the length that goes all around, and the deck area is just the length times the width for a square. So those are the perimeter is 96 inches, the deck area is 576 square inches. If you used a round or a rectangle, you just have to calculate what the perimeter and the deck area is going to be. There's nothing special about this 24. I'm just guessing at this point, estimating. What's going to happen? This is an iterative process. So I may find that 24 inches is too big, and I have to come back and start over, and I'll say 18. Or maybe I find out 24 inches is too small, so I'm going to up it to 36 inches. I don't know yet because I'm starting here, and design is an iterative process. You don't know what the answer is ahead of time, and so you may have to start over again and change your numbers a little bit. So square 24 inches, so that's why it's red. I'm choosing a shape and I'm estimating the length. Okay, so step 4, calculate the pressure required to generate lift. Okay, so now what I have from step 1, I said, well, I estimated my weight in that table was 3.03 pounds. I'm going to use 4 pounds to be safe. Again, we're trying to leave wiggle room for errors. What happens if I need another fan? And what happens if I need more batteries? I hate to design my hovercraft for 3 pounds, and I have to put another battery pack on that makes it 4 pounds, then my hovercraft doesn't hover anymore. So I'm going to conserve, err on the conservative side. So I'm going to say, let's use 4 pounds just to be safe. Okay, and that gives me about 30% wiggle room for adding additional stuff or so forth. So I'm going to use 4 pounds for this calculation. Okay, then from step 3C, I know my deck area, so I had 576 inches squared. So pressure, if you remember the units of pressure, is like PSI, pounds per square inch. It's a force divided by area. That's what pressure is, the force divided by area, just by definition. And it turns out the force is the weight of the hovercraft, and the area is just A. So my weight in my hovercraft is 4 pounds. I'm going to use a 4-pound hovercraft, divided by the area, which is 576. So I take pounds divided by square inches, and I get PSI, and I get 0.0069 rounding PSI, pounds per square inch, which is not much pressure. You think about that, right? You pump up your car tires to 30 PSI. This is not much pressure to lift this thing off the ground. And what you find here is that the bigger my hovercraft, the lower my pressure. If this was 1 square inch, I would need 4 divided by 1 would be 4 PSI. The fact that I have 576 square inches means I have very low pressure. So the bigger my deck, the less pressure I need. That's just the way it works. Of course, the bigger the deck, the heavier it weighs. So there's some downsides. But in general, the bigger the deck, the less pressure I need. So anyway, in my case, I have 0.0069 PSI. Now I have to convert that to inches of H2O, inches of water. And you have to go and you have to look online, and you can see on the online lifting fan module where this comes into play. This is an ancient unit of measurement. Like many systems in the United States, we have some old systems of measurement, and inches of H2O was used in manometers. A manometer is a device, is a U-shaped tube filled with water, and by measuring the height of the tube of water, you could in inches you could measure the pressure. You can Google it if you want manometer, but suffice to say that it's another unit of pressure. PSI is 1 unit of pressure. Inches of water is another unit of pressure. So I have 0.69 PSI, or equivalently 0.192 inches of water. Exactly the same thing, just different units, like centimeters versus inches for length. Okay, so that's step 4. Step 5, I got to calculate the gap area. So the gap area is a little bit hard to explain, so it's worth looking at this other video I've posted that goes over the nomenclature. But the gap area is you take the perimeter of your hovercraft times the height it's hovering, the gap height. Remember that 3 to 5 millimeters. That gives you the gap area. Essentially, this area is where all the air is leaking out. So air is being pushed by my fans, pushed down, and it leaks out under my hovercraft. And that little gap all around has an area. And that's the perimeter times the height is the area. So that's the gap height. So I get L from previous step, and gap height is what I chose from step 2. So I just multiply those two together. So I had a 96-inch perimeter and a 0.2-inch gap. And so I multiply those together, I got 19.2 square inches. So that's the gap area that my air is leaking out. So that's a calculation. There's no wiggle room in there. That's a rigid number. So that's the gap area, step 5. Now, step 6, I have to calculate the exit velocity or leakage velocity. This is the velocity that all the air is leaking out at. around that through that gap. So what I'm going to do there is equation 3.13 in the book. I'm not going to derive it because it's derived in the book. Suffice to say, this is the equation. VL is the leakage velocity. And basically, if I have my hovercraft, all this air is my little skirt. All this air is leaking out of the gap. Well, the stuff that's leaking out of the gap, that's all the air is leaking out. It's leaking out at some certain velocity. And that's called the leakage velocity, if it's uniform. We're going to make an assumption it's uniform. And I can derive the equation, but this is the equation in the book. And this tells me, given the required pressure, which I just figured out in PSI, what the leakage velocity is for my hovercraft. Where G is some constant, and G is the gravity, it's in inches per second squared. The gravitational constant, 9.81 meters per second squared, or 386 inches per second squared. And gamma, the Greek letter gamma, is the specific weight of air. And that has to do with the ratio of the weight of air to the weight of water, basically. Okay, if I calculate this out, I plug in my numbers, 4.182 times 10 to the third divided by the square root of the PREC, and I had that PREC was earlier, which we had was 0.0069 psi. That's PREC, so I plug that in, and I'm getting 348 inches per second. So that's the air. That's the velocity of the air leaking out. So this air is leaking out at 348 inches per second. That's pretty fast. So if I had a little anemometer, I could measure the wind speed. That's what we would measure. So that's the velocity of the air coming out around the bottom of my hovercraft. Okay. So step 7, calculate the required flow rate. Fine. This is when you go to size a fan, you need two things. You need to know how much pressure it needs to support, and you also need to specify how much air it can move. So you're specifying the pressure, PSI, or in this case, inches of water, and also the flow rate it can produce, which is cubic feet per minute. And those are the two things. Obviously, if I have a fan, you think about it. If I have a fan blowing a bunch of air and I obstruct the fan, so it has to generate a lot of pressure, it can't blow as much air. So you find that the higher the pressure, the less air the fan can move. The lower the pressure, the more air it can move. And that just kind of makes sense. Imagine taking your house fan and blocking half the house fan, so it has to generate a lot of pressure to overcome you blocking it. Well, less air is going to be moved. That's the way fans work. Okay, so the equation for this is Q is the flow rate, and it's called the leakage velocity, which we just calculated, times the gap area, which we calculated earlier. So Q, which is the standard nomenclature for flow rates in almost all engineering disciplines, the velocity times the gap area. So 348, which is what I calculated the last slide, and 19.2 I calculated a few slides ago from step 5. Multiply those together, and I get 6,690 cubic inches per second, or 232 cubic feet per minute. That's a lot of air. So my fan has to be able to move, or fans have to be able to move 232 cubic feet per minute. And that's going to be pretty big. So let's find out what we can do. So that's step 7. All right, so step 8 is find the appropriate fan, or if not, I'll iterate and start over. Okay, so let's go ahead. So I got to pick a fan. I can go to DigiKey or QuickFlow. Those are two sites. There are more, but those are two. We actually recommend DigiKey because it's probably the easiest place to get it. And that's the example I'll use. So digikey.com. I'm going to search for fans, and you search for DC fans, and you search for in stock. That means fans that they have currently in stock. You don't want to spec a fan and only to find out they don't have it in stock. So you're looking for something in stock, and hopefully they have a lot, like 50 or 100 or 300 or 1,000, because there are 100 teams in this class, and they're all going to be looking for the same fan you're looking for. So if there's 50 of them, you may get sold out. If there's 500 of them, the chances are you'll have it no matter what. So if you pick a fan, there's only 3 left in stock, you go to buy it tomorrow, chances are somebody else in the class has already bought it. So we're going to look for in-stock fans and 12-volt DC, because my battery pack runs off 12 volts. Now if you're using, for example, a 7.4-volt RC car battery pack, well then you're going to look for a 7-volt fan. If you're using 2 RC car packs in series, then you get a 14.4, you can look for something like that. So I'm assuming I'm using an 8-pack of AA's, which what I used for my weight estimate. That's 12 volts. Okay, so I'm going to filter the result by flow rate, and if you go into the DigiKey website, you can try it. It makes sense. You can go ahead and do this. I'm going to filter it by flow rate, and I'm going to choose somewhere between 80 and 120 CFM, just for example. You can pick all of them you want, but you get like 500 fans. 80 to 120 gives me like 20 fans I got to go through. I'm going to view page, I'm going to pick one. So what example, when I go through and I actually do this is the type of page I'm going to get. It's going to give me like 30 different results. It gives me the picture, great, all the fans look alike. It gives me the part number, yeah, okay, whatever. The main column I'm interested in is the static pressure. That's the most pressure it can possibly exert. In this case, it's saying 0.203 inches of water, 0.268 inches of water, 0.313 inches of water, etc. And so if you go back and remember, we needed 0.192 inches of water. Right, so this is the most it could do, just barely give us. So if we give it 0.1 in, if we chose this fan, it's probably not going to put out 100 CFM. It's probably going to put out very little CFM because we're close to the max pressure. This one's got a little more wiggle room, so I'll probably put out closer. Now this one's got a lot of wiggle room. I need 0.19, and it gives me 0.3. So I won't get 100. Maybe I'll get 60, 70, 80 CFM. So you're looking for a combination. This is the most it can put out. So you don't want to pick one that's right at your pressure limit. If I need 0.19, I'm going to pick something here that's like 0.3 or 0.4 or something like that. Okay. And so I searched around of those 30 fans. I found one I liked. Just to remind us, we're looking for 232 CFM and 0.192 H2O. And this is the data sheet for this fan. So it tells me as a function of air pressure in inches of H2O, so 0. This one puts out up to 1.8. Actually, it's about 1.4, looks like 1.5 maybe, inches of H2O. And it can put up to about 100 CFM. So it's giving me air pressure in inches of H2O as a function of airflow and CFM. So I need to find out for 0.192 inches of water how many CFM this fan will put out. So I take this 0.192 and I go over here and I find out where 0.192 is. So this is 0.3, so 0.15 is halfway. So 0.192 is probably right around here. So I come around 0.192 and I find out where it intersects my curve here. And this is the curve. This is the performance curve for my fan. So if I gave it 1.5 inches of water, I'm not going to get any air out. If I don't have to do any pressure, I'm going to get like 100 CFM out. So here I'm pretty low. So here I read down here and I read down and I get about probably 95, well, I guess. So at 0.192 inches of water, this particular fan will put out about 95 CFM. I need 232. I can only get 95. This fan ain't going to cut it. But what does turn out, if I need 232 and I have 95, well, I could use 3 fans. 3 times 95 is 285 CFM. That'll get me there. So I could use 3 fans. But I only estimated 2. If you go back to my chart where I estimated the weight of it, I only estimated 2 fans. That's not good. So what do I do now? Because I need 3 fans, but I'd have to start over basically. So what do I do now? Well, I could have a couple choices. Well, I could use 3 fans. It's a little bit heavy and costly. More batteries required, but it'll work. Remember, I also said I made that wiggle room. I said that the estimate was 3.03 pounds, but I used 4 for my weight. So I can go back and say, if I put a third fan in, am I still under that 4 pounds? If I'm still under that 4 pounds, then great. It'll work. So maybe that'll work. And it turns out that you would be. If you put that third fan in, you're going to end up with just about 3.75 pounds, something like that. So it still would work. So I could use 3 fans. Or, for example, I could use 2 fans. And if I change my desired gap height from 0.2 inches to 0.15, so I went from 5 millimeters, remember 5 millimeters was that worst case scenario, I went to 4 millimeters or 0.15 inches. It turns out I already did it, if you redo the calculations, you're going to find out that you only need 175 CFM at that same pressure. So now I have 2 fans that put out 95 each, so that puts out 190 for 2 fans. So if I only use 2 fans, this will hover. It won't hover as high as I wanted originally at 5 millimeters, but I get 4. And 4 is still good enough. Remember, I wanted 3 to 5 millimeters. So 4 millimeters is still good enough. So now I have 2 workable solutions. Well, I could use 3 fans and end up pushing that 4-pound limit for 3 fans, or I could use 2 fans and I hover a little bit lower than I wanted. But now I still got that 4 pounds to work with. So now if I need some more batteries, or my hovercraft ends up being a little heavier than I want, or whatever, now I have some wiggle room. If I use 3 fans, I have less wiggle room because I've used some of that weight, that 4 pounds. I've used some for that third fan. Or I could try reducing the weight. Maybe I'm not going to use 4 pounds. Maybe I'm going to use 3 pounds. Right? So if I can reduce the weight somehow by making things lighter, using cheaper or lighter batteries, I'll use lithium-ion batteries instead of nickel metal hydride. I can reduce the weight. Or I could go back, and this was just one of the 30 fans that showed up. I could go back and pick a different fan. It may be more expensive, but it may get a different performance. The fan I have to pick, this one is about $15 for fans. So I spent $30 for 2 fans, $45 for 3 fans. Okay. Remember, design is an iterative process. Just because you go through all the calculations once, it doesn't work out, that doesn't mean you can't do something. Well, I'll go back. I'll use 3. I'll change the number to 4 millimeters. And I actually had to go back and redo the calculations to get this number. So design is iterative. And when you go to the skills lab, you'll actually build an Excel worksheet that helps you do this. And you'll make your own worksheet, and you can say, okay, as I change the numbers, how do things change? So you don't have to go with your calculator and redo things over and over and over. Excel is a great tool for engineering. That's why we use it so much, because it allows us to set up the formula in terms of all these parameters. And then you can just change one cell and all the answers update automatically. So it's perfect. So go back and try it yourself.